Okay, guys, today we're going to talk about the real number set. And the real number set has two subsets, rational and irrational. So we're going to focus on those subsets and distinguish the difference between the two. So here we have the real numbers. So all of the numbers in this square are real numbers. Then we have the green square on the left and the yellow square on the right. And so all the ones on the left, these are all rational numbers. And you can see that there's even subsets inside of subsets. So our counting numbers, the numbers we first learned about, are 1, 2, 3, 4, and so forth, things you can actually count. Then we included 0 with the counting numbers to create the whole number set. Then we included the whole numbers plus their opposites to create the integer set. And then we have our rational set, which are all of these numbers, but they also include our fractions and our decimals. We're going to take a look at what a rational number is and what an irrational number is. So let's first talk about rational numbers. In the word rational, you can see the word ratio. So here we have the word ratio. So what it means, guys, to be a rational number is you can turn that number into a ratio, also known as a fraction. But remember, 0 can never be in the denominator. When we have a fraction and we divide it out, it will either be terminating or repeating if it is rational. Terminating just means it comes to an end, such as 8.21. It stops, it doesn't keep going. Repeating means we have a digit that keeps repeating, or digits. So such as 7.121212, we would also write that as 7.12 repeating. So a terminating decimal and a repeating decimal is considered a rational number. So here's a set of numbers that are all rational, and I'm going to go through and explain why. -1/2 is rational because it's written as a ratio. 6 and 2500ths can be converted into a ratio, a fraction, showing that it is rational. A perfect square, if we take the root of a perfect square, we get a whole number, and obviously we can place it over 1, showing how it is rational. Here we have 8, and we can put it over 1, showing that it is rational. 7 1/2 is already in fraction form, so showing that it is rational. And then we have a repeating decimal, which I will show you in just a few minutes, why 45 over 99 is the same as 0.45 repeating. So all of those numbers are rational. Now let's take a look at what is not rational and what is irrational. So an irrational number cannot be written as a fraction, and when we put it in decimal form, it goes on forever and it never repeats. So we can look at this number here and you can see it keeps going on and on, on and on and on. The dot, dot, dot just says it keeps going, and there's nothing that's repeating, and so this number is irrational. If I were to try to convert the square root of 3, a non-perfect square number, I would get a number that looks like this decimal. And the same for pi. We say pi is 3.14, but we know it really continues and goes on and on and on forever, and it does not repeat. So irrational numbers are those numbers that are not perfect squares, and they are non-repeating and non-terminating decimals. So when you describe an irrational number using these terms, you have to include both descriptors, non-repeating and non-terminating. Okay, so here's just a summary if you want to pause the video and write this in your notes. Now let's take a look at these numbers and classify each. Sometimes you must simplify before you classify. So we have the square root of 12. It is a non-perfect square number. It would go on forever without repeating. -3, we could convert that easily into a ratio. We just said pi goes on forever without terminating and without repeating. 2.173 terminates, it comes to an end, it's rational. Negative 3.276 ... is irrational. The square root of 49 is rational because it's really 7/1. Negative square root 196, since that is a perfect square, so negative 14, we could put that over 1. Negative 2 pi, that's still going to be irrational. The square root of 400, that is a perfect square, so we could write that as 20/1. 5.12 repeating, that's a repeating decimal. We could say 5 and 12/99, showing a fraction. Negative 2/3 is a fraction in itself. 4 and 12/100ths, okay, we can show as a fraction. 4 and 12/100ths. 4.5 repeating is also 4 and 5/9. The square root of 1/9 is really a perfect square because the square root of 1 is 1. The square root of 9 is 3. We have a fraction, 3/7. We have this number that continues without repeating, so I could never know its decimal place, its place value, to write it as a fraction. So that is why we cannot write a number that's irrational as a fraction, because we don't know the place value. Then we have negative square root of 3, that's not a perfect square. We have 2 times the square root of 3, that's not a perfect square. Now look, pi over pi is really 1, so we're going to show this expression is rational, and then 21. Okay, let's go on, and let me just show you the quick way of how to convert a decimal that is repeating to a fraction. So there is an algebraic way to prove this, but I'm just going to show you the shortcut, okay, the little 9 rule. So we have our whole number, so we're going to have a whole number in our fraction, and then we have a 3 that's repeating, and there's only one digit that's repeating, so we put over 19. Now we could simplify that, but we're just proving that it is rational in this case, so if you don't simplify right here, I'm totally fine with that. Okay, example 2, we have 4 and we have 0, 9, or just 9, but we have 2 digits that are repeating, 0, 9, 0, 9, 0, 9, so that would be 299, or 2 9s, giving us 99. And then in this case, we have 3 digits that are repeating, so we're going to say 999. So this is just showing how to convert a repeating decimal into a fraction, proving it is a rational number. Okay, the last thing we're going to take a look at is when we are either multiplying or adding a rational with irrational or rational with rational, all these situations, if you can get what kind of outcome you get. So when we have a rational plus a rational and we get a rational, I can show that as like 2 plus 5. Those are both rational, and I get a rational outcome. A rational times a rational, so we could say 1/2 times 1/4, and I get a rational number. Irrational plus irrational, so something like the square root of 2 plus the square root of 2, that's going to give me, so this is really a 1 here out front, so we're going to combine those coefficients and bring over the radicand, and I produce an irrational number. Okay, now let's look to see how in the world can we have an irrational plus irrational to produce a rational. Well, let's be creative here. If I have negative square root of 2 plus the positive square root of 2, so I have a negative 1 plus a positive 1, that's going to be 0. And so this whole thing gives me just 0. And remember, 0 is a rational number. So in this case, when you do a rational plus irrational plus irrational, okay, in this case, you could get either outcome. When we have irrational times irrational, we can get either outcome. So here, if we have the square root of 2 times the square root of 3, the square root of 2, I'm so sorry, we're trying to get a rational number, that's going to produce that perfect square, which is a rational number. Now let's do irrational times irrational again, but we can see that we can get an irrational outcome. So these two can be either outcome. Now, if we have rational plus irrational, so let's just say 2 plus the square root of 2, we can't even combine that together, so we just get 2 plus the square root of 2, showing irrational. Now we have rational times irrational, and we want to get rational. So let's use 0 times the square root of 2, and that gives us 0. So we have a rational times irrational to produce rational. Now let's do rational. So let's just do 1 times the square root of 2, and we get the square root of 2. So here's another pair that could be either outcome.